Today, we have a much anticipated topic, which I must admit to you, I'm a little bit nervous about cracking open, because black holes are some of the most misunderstood ideas that we have in astronomy. There's some of the least understood ideas as well. And I think that there's a tremendous amount of misconceptions about it, only rivaled by relativity, which plays heavily into how we end up with our conception of the black hole in the first place. So what I'm going to try to do today is answer the fundamental question, what is a black hole? And we'll see if I can come up with an answer for that for you by the end of the class. So we'll do that in a couple of ways. First, we'll just recap what we talked about with general relativity last time, because this is the fundamental theory upon which we get our standard interpretation of the phenomenon that we call black holes. So, fundamentally, a black hole is an event. It's an appearance of some sort of phenomenon which we see in the universe, and it boggles our minds as astronomers because it doesn't fit into our ordinary conception of how matter and light should behave. Yeah?
I remember the theory was originally by Stephen Hawking, correct?
Stephen worked a lot on this topic, yeah. Kip Thorne, there's... I don't know the answer to that, actually, because...
I think we took a picture of one the year after he had died.
Oh, we'll talk about that. We'll talk about that.
Also, I remember hearing that if all of Earth was supposed to be a black hole, it would be the size of a grape.
Oh, what? A grape, yeah, that's true. Yeah. So we'll play with that. We'll talk about that supposed picture. I say supposed because it's a bit more complicated. Actually, there was a Japanese group that published a paper right afterwards that analyzed the data in a very different manner. And so we'll look at both perspectives. You may have noticed that despite the fact that your textbook updates automatically, actually it updated while I was in the middle of reading it, which was quite interesting. I was in the middle of quoting a section that disappeared, which was quite fascinating. Which I don't know how I feel about that, honestly. I wish that as it updated, it would give you like a list of changes that it made or something like that. I feel like that would be a little more fair. Anyways, what I wanted to say is you may have noticed that picture was conspicuously absent from your textbook. And I think there's a reason for that, and we'll talk about it. But OK, where was I? So we see something in the sky, and we call this thing, this event, this appearance, this contradictory appearance, we call it a black hole. And so we'll start with that, and we'll sort of break down the theory. We'll see how general relativity leads to this. And then we'll look at the evidence for black holes. And then I want to close out by informing you about some interesting alternatives to the general relativity explanation for black holes, which are actually starting to proliferate. There's a number of different other possibilities to explain these phenomenon in the sky, which don't necessarily involve breaking the laws of physics as we understand it. And I think those are quite interesting. So that's the general pattern that we're going to move through. And my goal here is really to explore this phenomenon with you and try to make sense of it a little bit better. There's been a great deal of popularization of the very mystical, spooky side of black holes. Your textbook has enough of that. And of course, you've probably been beaten over the head with it by the popular media if you pay any attention to science news or anything. So I won't necessarily reiterate a lot of that stuff. But I will try to explore the gaps in our understanding, because I think that's where real developments are going to happen. we were talking a little bit before class about Plato's allegory of the cave. And astronomy seems like it's one of the best cases of this playing out, where we see things and we don't know what they mean, right? We can only see things that are bright, things that are hot. And so all of our stories concern that. And of course, in Plato's allegory of the cave, there's something happening outside of the cave. It's casting shadows, right, on the wall, and the people are trying to interpret the shadows and make stories up about what could possibly be happening outside of the cave. And sometimes when we do that, we're incredibly misled, of course. Now, this is played out over hundreds of years in science. We tend to think of science as this incremental improvement in our stories about what these shadows mean. And so we've reached the bleeding edge of what is known about the cosmos as far as astrophysics is concerned. We've told the story, we've told our best story of how stars metamorphosize, how they, I don't think evolve is the right word, it's more of a cyclic metamorphosis, right? How they grow and collapse and turn into dust again and fuse these heavy elements in their explosions. And so we've kind of reached the edge of what we know about that. Now, we talked a bit last time about neutron stars, which is, of course, this one potential remnant after a supernova, which is thought to be this very, very, very highly compact form of matter, where essentially the atoms have not only lost the form of their electron shells, but their nuclei have also begun to sort of melt together, and you get this very, very dense object. And the signatures of neutron stars, right, the way that we know that they're there has very, very much in common with black holes. In fact, it is spectroscopically and empirically almost impossible to distinguish a neutron star from a black hole, the main difference being that the gravitational forces associated with the black hole versus the neutron star are much greater. So we'll deal with that. So let's just refresh our memory just really quickly. So we talked very briefly at the end of class last time about general relativity and this idea that Einstein came up with, which we call the theory of general relativity, which, in my estimation is less of a theory and more of a highly, highly precise description of what's happening physically in the universe, right? How things with mass, let's say bodies with mass, how they change their trajectories in the presence of one another. Now, Einstein formalized his ideas into this concept of space-time. And of course, space and time is a dynamic concept, space being a series of coordinate locations, so essentially where bodies are located with respect to one another, or really just with respect to some coordinate system that you've coordinated off. And then time is, of course, the dynamic aspect of that, how change happens, where this is in the process of change.
So black holes like warp space and time. That's so what we're working towards, yeah. Right?
That's what we're working towards, yeah.
So it is a warp in space-time, that is basically just a giant dip. Could light still get out if light travels in straight lines? Or is it just that light could theoretically get out eventually, it's just that the warp is so deep that it just takes so long for light to get out? Or is that the basis for Stephen Hawking's multiple dimensions theory, in that it essentially goes into the upside down, if you will, and it goes out the white way?
So
if that makes sense.
I will answer that question, but let's get into the structure of these things, because the formalization of the theory allows for the idea that, of course, beyond some threshold, the light would not be able to escape. But outside of that, of course, it's bent in such a way that you get something like a ring structure around it as well. Now, there's a couple of things that you brought up, though, that are interesting. Warpage is a material science concept, right? We're talking about deformation of an object, right? I think that there's something really dangerous that has happened here when we start to apply physical concepts, material concepts to ideas, right? If I say that, if I say to my wife, my love for you is a little bit warped right now, what does that mean exactly, right? Okay, so my point is that there is serious danger when we start treating ideas as if they're bodies, as if they're material objects that can be subject to material processes. Now, it works great in poetry, and it makes for very, perhaps, rich analogies that can help guide our behavior. But I think a lot of the confusion and the reason that we haven't been able to make complete sense of these phenomena that we call black holes comes down to the fact that Einstein's description of reality involves this dynamic concept called space-time, right? What do I mean by dynamic? I mean that it's not a static body like a table, right? It doesn't have a shape like a table. It doesn't have a form, a structure, because it's in motion. It has a dynamic component to it. And the problem is that makes space-time not a material that is actually subject to material changes, right? And so when we start applying these material, physical ideas like pushing on space-time, pulling, twisting, warping, we are moving into the realm of analogy and poetry, and we have left the realm of hard material science at that point. And, you know, I've read a lot of Einstein's primary work, and I've read a lot of his letters, and I don't think that Einstein would be very happy with what people made of his ideas and how they began to churn this and treat space-time as a physical material. I think he would be very upset about that because I don't think that's what he was trying to say. We'll get more into that later, but one consequence of treating space-time as an object is that if space-time is now treated as a fabric, right? We've poetically treated a dynamic concept as a fabric. Well, if it is the fabric upon which things play out, then of course one consequence of that is that not only should bodies be moving in non-straight lines in the presence of large other bodies, right? But also light itself should be bending around, okay? And so the fundamental question is light actually affected by gravity? And I'm not sure that to my own satisfaction, that question has been answered, because there's a number of contradictions to that idea, which I pointed out to you last time. In particular, that the initial evidence and really the follow-up evidence for light being bent around our own sun only occurs in a very small region around the sun, which, you know, I guess what I'm trying to say is it's very difficult to separate out whether light is bending due to gravitation or whether it's bending due to some material interaction that's occurring in the limb of these bodies, right? Because ultimately, where there is mass and gravitation, there's also atoms that are engaging in interactions, in photonic interactions, right? You know, I want to also bring up the concept of boundary conditions in theory as well, right? So, you know, regardless of whether gravity is actually affecting light or whether it's actually the stars themselves that are affecting light, which seems mathematically congruent by certain renditions of the theory, we come up with this idea when we get around to black holes that if we take relativity to its extreme consequences, then at some point we reach a point where the gravitational effects become so strong, the deformation of this space-time stuff, this idea, is so intense that it reaches an infinity, okay? Now, this infinity is troubling. It's always troubling in science when you have an infinity fall out of your formula. And in fact, 100% of the time when we find infinities in science historically, they have led us to the conclusion that we've misconceived something terribly. So I'll give you an example. There was a big famous version of this called the ultraviolet catastrophe that occurred around the the early days of studying black body theory, which we dealt with at the beginning of the course. And what happened was people realized that if you decrease the wavelength of light, the energy goes up very nicely, and you can fit a curve to that. You can fit a nice curve to that. The problem is that it predicts that at small wavelengths, particularly at ultraviolet wavelengths, the energy of the light should go to infinity. Well, it doesn't, right? It's very clear to see that ultraviolet light doesn't have infinite energy. In fact, infinite energy doesn't even really make sense to us. And so people were really in crisis about this for a few years. There wasn't the same kind of popularization of this idea, right? There was nobody making spooky renditions of this at the time because it just wasn't as well known of an idea. But what was cool that came out of this infinity was that people realized that actually light in this one particular region does obey this particular mathematical law. But something happens at the next level. There's a boundary to that mathematical description of reality where things change. And Max Planck came along and actually said, you know what? I think that we can fit the data if instead of treating light as this continuum of impulse, we actually realize that light occurs in discrete impulses, which we now refer to as the photon. So Planck quantized light into these little packets. And when he did that, what he realized was that he could modify the formula for black body radiation in a way, introducing this idea of the quanta, that eliminated the infinity all of a sudden. And this was a huge victory. Of course, our entire conception of how light works is now based on the photon, right? This was a massive realization, but it wouldn't have happened without this terrible crisis in physics, which centered around the ultraviolet catastrophe. And I think what we're seeing with black holes is very much a similar catastrophe, actually, where we're taking Einstein's very, very precise laws, just like the formulations of black body radiation were very, very precise at the time, but we're extrapolating them beyond their boundary conditions to a point that we're making inferences that are outside the bounds of that formula. And it's going to take somebody to come along with a really bright idea of how Einstein's theory of general relativity breaks down at a certain point, and something else needs to take its place. And so this is an enormous topic of research for the quantum theorists, because the biggest problem in physics, I feel confident saying that, is that general relativity does not work at the atomic scale. There is no way to apply the principles of general relativity to the atom itself. And we have a very, very good mathematical description of reality at the atomic level. That's called quantum theory, essentially. There's a few different formulations of it. And those two theories are incompatible with one another. And nobody has figured out how to bridge the gap yet. And so, hopefully by the end of this, is looking at what a lot of quantum physicists are proposing as solutions to the black hole paradox, which don't involve the breakdown of space-time and so forth. And those are quite interesting, and ultimately they're going to involve, just like the neutron star, a lot of these formulations have to do with formalizations. They have a lot to do with new types of matter, new ways that the atom can, new shapes the atom can take on, new ways that it can compactify and produce these sort of gravitational effects. So at any rate, this concept of boundary conditions, I think, is something that's really, really important. And all scientists are aware of this. I think I mentioned I'm actually publishing a paper right now where I'm trying to describe a new way that water behaves under certain conditions. And this idea of how things can behave under different conditions is the idea of boundary conditions, right? It's the idea that in certain contexts, molecules, in my case, waters, can behave completely unlike waters would behave in your everyday life, say, from the drinking fountain or something. And so when you really get into the edge of what's known in science, you have to constrict your ideas to certain conditions, because the environment changes and it's reflexive and there's a feedback loop that builds up, and the physics can lead you into completely unknown, unpredicted zones. So we'll come back to this boundary conditions idea a little bit. Now, I'm going to move past this. So, okay. All right, but let's explore for a moment this idea that is proposed about the black hole, what is actually being said. So if we take Einstein's general relativity to its extreme consequences, we do end up with this point at which the mass becomes so great that light and anything else can't really escape from the depths of what we would maybe poetically call a gravity well. Now, I actually want to take a moment to point out something very interesting also about relativity. Relativity treats mass, the concept of mass, and the mass of a body as if it is a point at the center of that body, okay? This is really interesting because all the story we've told of stellar collapse right now concerns all of this material crushing down on the center of a star, right? And this intense gravity that is these intense gravitational forces that are appearing at the center of the star. And this seems like an incomplete story to me because, you know, let me ask you this. If I was to cut a hole in the Earth all the way down to the center and I was to drop you into that, what would you feel at the center of the Earth? Would you feel a lot of gravity or a little bit of gravity? None, yeah, right? Because at the center of the Earth, you would be getting pulled from all directions, right? And so, I could be wrong about this, but it strikes me that this is something which general relativity sidesteps to some extent. Because by treating a whole body of material as a point, you are in some ways avoiding this complexity which results from atoms pulling you from all directions. And I wouldn't be surprised if our entire story of core collapse is a bit more complex than the one that we've told so far, in which fusion is not restricted to the core. And maybe this whole story that we've told will be very different in 10 or 50 years from now because we haven't really thought too much about these onion layer types of confinement situations. And NASA's just started cracking open the topic of lattice-confined fusion, which is essentially this idea that you can smush atoms together inside of a lattice, right? Inside of a cage of other atoms. You can squish them, and you can do it at pretty low temperatures, actually. So you can do it at room temperature, as a matter of fact, by essentially squeezing that brick, those layers, with pulses of light. And I'll be very curious to see how that model begins to work its way into the astrophysics. Okay. But for now, let's entertain the idea that the mass can be described adequately with point particles. If we do treat mass as being a point, then, and we use Einstein's ideas, then, oops, I skipped a slide. Then we're essentially going to end up with this idea that as the core collapses, as these bodies keep pulling, as the atoms keep pulling on one another, they're going to get so compact and so dense that their gravitation is going to overwhelm everything. So, you know, this isn't actually a ton of material, right? It's something like a star who, in its final stages, has something like 3 times the mass of the sun. It's not too much, right? But of course, that material is crammed into a tiny, tiny space. So when this star that's like 3 times the mass of the Earth has been squozen down to something about 20 kilometers wide, the velocity required for anything to escape from it essentially is unattainable. It will never be able to reach that escape velocity. And one thing that's interesting about escape velocity is it doesn't really depend on the mass of the smaller object, right? You need to throw a pencil and a rocket at the same speed to get it off of the Earth, which is quite fascinating. So, if this collapse continues, at some point you reach a point where the escape velocity exceeds the speed of light following from this formulation. And this is where we really start to get into the idea of an unreachable point in the universe where no probes can return, no light can even return from it. And this is how we end up with the idea of a black hole. This was actually popularized first in the 1960s, actually by John Wheeler. And, it's kind of an old idea, actually. There was a Cambridge professor named John Mitchell who wrote a paper in 1783 about this idea that stars with enormous mass could achieve escape velocities that were equivalent to light. Actually, in 1796, Laplace, who gave us our nebular theory of planetary formation, also made a similar proposal. He actually used Newton's theory of gravity, and he determined that these resulting bodies, he called them dark bodies, which I think is quite interesting. And we'll come back to that because some of the quantum formulations also produce dark bodies as well. So, like you said, as you can see in this picture, at some point, there is a point at which these, according to relativity, the fabric of reality is distorted in such a way that light itself can actually not make its way out of this object, and it actually begins to circle back upon itself. And, this point at which the star's geometry cuts off communication with the rest of the world is a boundary, and it can be mathematically determined based on this escape velocity principle. We call that the event horizon. And that calculation was actually worked out by the mathematician Carl Schwarzschild, and it's often referred to as the Schwarzschild radius, this dimension. And this was actually derived essentially as a solution to Einstein's equations. And like you said, if we were to smash the Earth down to the size of, I don't know, a penny, a grape, you could also achieve a situation where light would no longer be able to escape from it, which is a tantalizing idea. And what happens inside of that? What happens underneath that event horizon has been the subject of of enormous speculation and tantalizing fictions. There's so many great movies, right, about the consequences of reality being skewed beyond the event horizon of a black hole. And, I think there's a reason why those narratives are so appealing to us as well, because something very strange happened during the Enlightenment years. For the first time in the history of humanity, which dates back maybe 1 million years, I don't know, maybe hundreds of thousands of years at least, for the very first time, people were standing up and saying, I don't think that the universe works magically. Right? And you might think, oh, that was a huge relief, actually. But I don't think it is a huge relief, actually. I think that we really, 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 really need magic in our universe. We really need it because it gives us hope about what could be. It gives us this sense of possibilities. And, I think the idea that magic could be subsumed into rational explanation, into science, is such a tantalizing possibility that its attraction knows no bounds in some sense. And I would normally be all for that, but I think that it's a little bit misplaced because I do think that there's a lot of magic in the universe. I just don't think that it is in physics is the thing, right? Physics is a pretty boring subject when you think about it. It's really just the interactions of bodies with one another at the end of the day. And you might say, yeah, well, light, that's not a body or something. And I would say, well, actually, light is probably an activity that's occurring between atoms that are essentially touching each other in some way or another. So I think that physics is a pretty boring subject in that sense. I think that the real magic actually is occurring in biology, right? I mean, where does an idea come from, for instance? Right? You have ideas all the time. Where is that coming from, right? Where does love come from? Where does compassion, heroism, persistence, determination, right? There's a lot of magical qualities that just really don't have anything to do with physics. And so I think that the only reason I'm even sort of standing here with some skepticism towards the introduction of magic into physics is that I think it's the wrong venue for the art form, right? I think there is a lot of magic in the universe, and I think that it can be folded into science, but I don't think that physics is the best place for that. And something strange has happened, too, in the last 100 years or so, where physics is essentially treated as the king of all sciences. This is maybe a new thing that's happened, and I'm not quite sure why that happened, but I noticed it very quickly. My wife was in a microbiology lab when we were in New York at Columbia, and she was working on the electron transport chain inside of these bacteria. And she had a discussion with her boss one day about the electron transport chain. And she had just some very fundamental questions like, well, what does it mean that an electron is being handed off amongst all of these molecules in this respiratory chain? What is actually happening? What are the atoms actually doing to one another? What does it mean for an electron to pop off of one and go to the other? And the answer was, that's not our problem. Go ask a physicist. And so, of course, we go and ask the physicist, right? My advisor was a physics professor. And we talk to physicists, and the physicists, we say, well, what does an electron look like? What is it actually, what's happening here? And they give you a series of equations. And you're like, but these are dynamical solutions. These are telling me about the activity of something. These are telling me about some motion that's occurring. They don't give me any idea about the structure of this phenomenon. And they say, that's not our problem, that's a problem for the philosophy department. Well, you go to the philosophy department and you say, can you help me understand what charge means? What is actually happening during charge? And they say, that's a problem for the physicists. And so it's this crazy toss game where people are kicking these problems around, and nobody's really grabbing it by the horns and trying to answer these fundamental questions. And so I guess what I'm trying to get at here is I don't think that physics really is the king of the sciences. I don't think that any one of them is actually king. I think it's more of a congress in which people are actually have different perspectives that are equally valid. And there's not enough crosstalk between them. I imagine that the ideal utopian academy of the future will have a great integration of the departments that come together and actually are able to review one another's ideas and contribute meaningfully. But that doesn't seem to be the case yet. So maybe your generation will fix that problem for us. OK. So, right. So the calculations following from general relativity predict that in these stars, which are of sufficient mass, this core collapse continues and continues, and it eventually forms this infinitely squished point, a point which they claim has zero volume and infinite density. Right? This is essentially what happens when you take that curve of pull versus radius and you extend it out to infinity. You get to a point where you have essentially zero radius and all of your mass is crammed into that. Okay. So, there's this quote from your textbook. We do not yet have the physical understanding or the mathematical tools to describe the singularity itself. And the singularity is, of course, the point where this infinity occurs in an equation. Or even if the singularities actually occur. From the outside, however, the entire structure of a basic black hole can be described as a singularity surrounded by an event horizon. So I think this is actually, I was actually quite surprised to find this sentence in the textbook, and I think that it's rather astute. And I think that your textbook actually, and we'll get into this more as we go along, I think that the textbook is written in such a way that recognizes that this story is incomplete. And this being a textbook that automatically updates itself, it will be very interesting to see how this story changes in future years, because I think there is a sense that this is not a totally finished story. Now, there is something really, really interesting happening in these objects, and so we're going to look at some of the evidence for what we see in the sky next, and it's very intriguing. And one of the stories that we're going to look at is the story of gravitational waves, which has been a huge new science which has opened up, and it's got some very intriguing evidence that points at the idea that there are some sort of super gravitational objects, let's say. There's some sort of very strong gravitational influences that do appear to be out there surrounding these things that we call black holes. So the details of whether physics is actually breaking down at these things or not, I'm a bit more skeptical of, but there does appear to be something really interesting happening out there. And it's our job, of course, as scientists in the future to make sense of that. Now, let's check out the evidence for these things. Cool. All right, so how do we go looking for something that's light years away? It's only a couple dozen kilometers across, and it's completely dark, right? Because in astronomy, we generally look at things that are bright or hot. And we're not going to see anything bright or hot when we're trying to find these. Well, the first thing that people started doing, right? So black holes, like I said, in the 70s and the 60s, they fell out as a natural solution to a singularity in Einstein's general relativity, right? If you push the circumstances, the conditions of general relativity far enough, if you put enough material in a small enough space, in this case, an infinitesimal space, you end up with some crazy revelations. Well, how do you go looking for that? Well, you can start by looking for a star whose motion doesn't make sense, right? A star that appears to be perhaps orbiting something that you can't see, right? And we talked about this a bit with the neutron stars as well, because neutron stars are, of course, very, very tiny. And so our evidence for neutron stars starts off in much the same way. We're looking for some sort of Doppler shift of the spectral lines. If you want to recall back to our lecture of determining these binary systems and analyzing these binary systems, we can often look at the wiggle of the stars to make sense of the companion's location and dimensions and so forth. And so that's how our search for black holes began as well. Now, just because you see a big star that's wobbling and there's nothing there doesn't necessarily mean that there's nothing there, right? It doesn't mean that something's invisible. Of course, you could have, its light could be outshining its partner. There could be a lot of dust there. But, and it could be a neutron star as well, which we've talked about. But the fundamental defining feature of what we call black holes is that the gravitational influence of that body appears to be too strong to be a neutron star. In other words, under our current understanding of how matter behaves at the quantum level, the neutron should no longer be able to sustain that kind of gravitational pressure at that point. So I think this is a really interesting point. A black hole is essentially a neutron star which is too big. And that is what we see when we look out at the skies. We see a very similar appearance that we would generally ascribe to a neutron star, but the gravitational influences are just too strong, right? It's wobbling its companion star too much to account for it as a traditional neutron star. Now, that could mean that we misunderstand neutron stars, or it can mean something entirely different is there. So like neutron stars, we also see a great deal of X-ray evidence coming out of these, right? We talked about these fast bursts of X-ray and gamma radiation. We talked about the pulsars, which are a particular breed of rotating neutron stars. The black holes are, of course, going to have the same characteristic, right? Again, they're very, very difficult to distinguish from neutron stars, except for the fact that they're too freaking big. All right, so like neutron stars, we also have a case where the infalling gas whirls around this point and creates a pancake of matter, which we call an accretion disk. And so this is the friction that's actually happening as it falls in is leading to this X-ray production, which gives us something else to look for when we go out into the sky. So, you know, there is some suspicion that we might be able to delineate black holes from neutron stars based on the quality of those X-ray emissions, but it's not so simple, right? There's been a number of papers that have tried to find distinguishing characteristics in the spectral features of black holes versus neutron stars, and they're able to do it in some cases. The one that I read was able to do it in maybe like 2 out of 6 cases, but there was a great deal of overlap, and so that seems to be an ongoing project to actually determine whether you can say, okay, here's the fingerprint of a black hole versus a neutron star. And we're not quite there yet. So the first black hole that was actually, you know, fit the bill, let's so to speak, in terms of the way it was behaving was this guy here. And you have a little dot there to show you the size of our sun. So this is Cygnus X1. And this was actually studied by a number of different researchers back in 1971. And it's actually the strongest source of X-rays that we have that we can detect from Earth. So something big is going on here. Now, the visible star is a type O star. It's very, very bright and big. And the measurements of the Doppler shift of that star showed that it had some sort of unseen companion. And when we did the mass calculations on that due to its displacement, we found that that companion should be about 15 times the size of the sun. So therefore, this companion's too big to be a white dwarf, and it's too big to be a neutron star. Now, it's very, very difficult to say much more about it, especially back in 1971, because this is what you actually see over here when you look at this binary system. And actually, I believe, I can't confirm this for certain, but I think there's a number of stars actually involved in this system. Just like most stars don't occur in a singular scene like our sun, right? We're a very, very unique solar system that only has one sun. That generally doesn't tend to be the case. So this is a very, very bright apparition in the sky. And, you know, sussing out the details of that is no small task. But something's happening there. There's something big. Something's tugging on this star, right? And we don't know what that is. And so we apply these, the formulations of general relativity, and we say, well, it's dark because it's so big, light can't get away from it. Okay. A little lag here. Apologize. Come on. All right. So I want to talk to you about gravitational waves a little bit, because up to this point, our main metric for studying the stars has involved light. And this is a terrible metric to understand black holes with because they're dark. Now, another feature that falls out of Einstein's conception of gravitation is that these tugs, that as bodies move, particularly in binary systems, as they're changing their location, that the tugs of gravity will occur in pulses, right, in respect to this rotational process, right? As it gets closer and further away from you, you're going to experience more tugs, right? And so this pulsating tug is what has been deemed a gravitational wave. And so people began to dig into ways of detecting these tugs. And so the way to do that, of course, Einstein himself said, you know, you'll never ever see these gravitational waves because they're so weak. The differences in the gravity due to these minute variations in location are so small that we'll never be able to detect them. Now, Einstein didn't know about neutron stars or black holes or anything like that at the time. And so, of course, the idea of a supermassive star in one location was beyond his conception. But it turns out that with the advent of the discovery of neutron stars and these compact high-mass objects like the black holes, it became possible to obtain a source that was capable of expressing gravity in a varying way that would lead us to potentially be able to detect those gravitational waves. And so, you know, this idea was actually, it had actually been around before Einstein to some extent, although it fit with his formulation. So Oliver Heavisides, who doesn't get enough play in the science textbooks, actually proposed this idea in 1893, and Poincaré in 1905, suggesting that they would essentially be just like electromagnetic waves, i.e. light, but they would have the opposite effect. They would be a tug sort of thing, whereas light is more of a push, right? Which I think is really fascinating. And actually, the mathematics of gravitational waves is almost identical but inverted to light, which I find absolutely fascinating in terms of understanding what light and gravity really are. Because the more that you study light and gravity, it's impossible to ignore the idea that they seem to be two sides of the same coin, right? Gravitation, let's think about light. It's a transverse wave. What does that mean? It means that it's something like a torsion, right? When you have a material and you twist on it, you get a shear deformation, which is transverse. This is the idea that the deformation propagates outward as the thing moves forward, right? Light also has this sort of helicity to it, right? Photons twist as they move. Gravitational waves are exactly the same, except it's a tension as opposed to a push. Light has a forward momentum to it. That's how you get these things like light sails and these really cool inventions people are imagining for it. You can actually push objects with a laser, it turns out. Well, gravitational waves are the exact same thing, and they're very much like inverted photons in this sense, and I think this is absolutely fascinating. You know, one of my favorite physicists of all time, this gentleman who was, he's now an emeritus from Caltech, and I've gotten relatively close to this gentleman recently. I had a chance to hang out with him when I was in LA over break. And he reformalized Maxwell's equations in order to simplify them. And one consequence of doing that he found was that you can actually make a lot more sense of light if you treat it as a transaction between two atoms. In other words, light doesn't just get emitted from one atom and received by another. The receiver is also taking part in the emission, and the emitter is taking part in the reception. There's some sort of handshake that's going on between these atoms. And I think gravitational waves, the theory surrounding them really plays into this paradigm, which is really fascinating. So how do you detect a gravitational wave on Earth is really the question. Well, the idea is that, you know, the detector, the person who's trying to observe these waves, is going to feel some effect of the distortion. You know, one way to think about it in Einsteinian terms would be the distortion of space-time. Another way to think about it would be that their instruments are going to feel some sort of strain that wasn't there before. And this can, you know, a strain on an object, if I was to take a rubber band or something and strain it, it's going to stretch, okay? And so the basic idea was to set up a series of arms, very long arms, where you could measure the stretch of those different arms, and you would have them at multiple locations around the globe, so that as those waves of gravitation from some distant high-mass object, some moving objects, we're generally looking at merging neutron stars or black holes, that those will be felt simultaneously, you know, not simultaneously, but with some slight delay, depending on which part of the Earth is felt first. And so what kind of distortion are we talking about? Well, it's very, very, very small. So the idea is that these rotating stellar remains, right, these neutron stars or black holes, are going to radiate this energy away in the form of gravitational waves. And this is actually going to contribute to those stars coming together and eventually merging. And that we should be able to see that decrease in their orbit in accordance with the radiation associated with these. Radiation is a terrible word to use here, but this inverse radiation associated with gravitational waves. And it's something like their orbits will decrease by a 10 millionth of a second per orbit. And this is actually one of the first things that kicked people off to the idea that, yes, this actually did seem possible. So they were able to detect these minute variations in the orbits of these bodies long before they went ahead and built these detectors, which were very expensive and elaborate. So that was, I think, the fuel that they needed in order to get the funding together to build this enormous apparatus. So this is essentially the scheme for the gravitational wave detector, which is, it's a variation on a theme which has been present in physics for a very long time, which is something we would generally call an interferometer, right? And interferometer, excuse me. And what you're actually looking at is you're trying to measure very tiny changes in distance by looking at the way that beams of light will interfere with one another. Now you can think about this interfering process in that, of course, light we talked about has these pulses of push and relaxation, right? It's a pulsed push. Well, it turns out just like sound also has these pushed pulses. And the way that, something like noise-canceling headphones work is they sample they sample the environment, they invert the phase of that push so that all of a sudden your speaker, instead of pushing air to your ears, is actually relaxing at the moment that that noise is coming in. Well, in that sense, it can cancel the noise because you actually get a null spot in that wave where your ears are getting told to relax at the same time that they're getting the excitement of the noise, and the result is noise cancellation. So interferometers work very similarly. You have a laser, let's say. You have a mirror at one end. You shine your laser. It comes back to your detector, let's say. You can use a special kind of mirror that splits it and goes to a detector, lets some of the light back through. What you can do is if you change the length ever so slightly, now that wave pulse is going to return to the original source in just the way that that push is going to be canceled out by a relaxation in that light pulse. And you can measure, by doing some calculations, you can actually determine how much that length is contracted. And so this is the basic setup. You're looking for a contraction of these two arms. Now these arms that they built there's several different locations. Let me see here. These are 4-kilometer long arms, right? So really, really, really big detectors. And they're looking for tiny little motions. I don't have the figure in front of me, but on the order of microscopic variations in the length of these as the gravitational waves were predicted to pass over them. And ultimately, as the waves pass over them, these arms are going to feel the strain of that gravitation, and they're going to contract and stretch accordingly. Now, here we go. So the variations that were expected to be detected from the results of some of the biggest events that we even know about in the universe, and I'm talking about the coalescence of 2 neutron stars, or the swallowing of a neutron star by a black hole, these huge, massive events. The sort of change in this 4-kilometer long barrel was on the order of a 10,000th the diameter of a proton. Really, 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 really tiny influences from these distant events, okay? And so interferometers are perfect for this because the wavelength of light being so small that you can actually see these disturbances that are sub-microscopic. So this is pretty cool. These are really, really accurate detectors. And back in 2015, they finally had this thing operational, and almost instantaneously, well, very quickly, they discovered that they could correlate some of these waves that they were receiving with some events. So they had their eyes on a particular high mass event out there. And what they found was that this one particular black hole merger event that they had their eyes on was correlated to this wave that was detected first. Let's see, where was the first one? The first event was in Louisiana. And then 7 seconds later, it was detected in Washington, which is just the distance given by the speed at which these gravitational waves travel, which is, of course, the speed of light, which makes sense, being that it's sort of the inversion of light. And these two signals overlapped almost perfectly. And so people celebrated, cracked open champagne, and essentially announced that they had detected gravitational waves empirically for the first time, which is, you know, a very attractive proposal, and I think it's quite intriguing. So they kept this project going. They've still got it going. In 2017, they had another detector called Virgo, and they were able to actually triangulate some of these detections and look at neutron stars. They found even smaller neutron stars, stars that were only maybe the size of our sun, essentially. And they were able to track the actual position of these with respect to the gamma rays and X-rays and triangulate where these gravitational waves were coming from. And it seems like one of those situations where the more they look, the more they're actually able to confirm that what they're seeing is originating from these distant events in the sky. And I think that's really the hallmark of a great experiment, is that you're able to continue to pull out new events, right? You don't just have one event that you claim, okay, well, we're done here, right? They keep going, they're still going, and they're still finding these. And this merger, actually, that they detected in 2017 was of course, visible in the gamma ray spectrum as well. Now, one thing that's really interesting is they were able to detect that that the shell that was being emitted from these was really high in these heavy elements. Something like 200 Earth masses of gold were detected in the spectrum, right? That's a lot of money if you could find your way to get to it. And around 500 Earth masses of platinum, right? So there's a lot of good stuff out in space if you can make your way to it. Unfortunately, this is many, many light years away, so that wasn't going to happen. So this is, I think this is a pretty cool figure from your textbook that shows the catalog of all of the different events that have been observed with these gravitational waves since then. And I think this also does, and these are almost all mergers of different neutron stars or black holes. And I think this does a really good job of showing you the crumbling line between neutron stars and black holes because, you know, it's very much on a spectrum of mass here. And I think that, you know, this is, for me, one of the more compelling pieces of evidence that something interesting in the realm of gravitation is happening at these places that we call black holes, right? There does appear to be something happening there that has to do with gravity. There's something massive that's out there in these locations. Now, the question of whether that is a breakdown of physics or whether that's something that we haven't thought of yet, well, there's some interesting possibilities which I want to crack open to you in the back few minutes of this class. I do want to address this photograph of the black hole, which was, like I said, was conspicuously absent from your textbook. I was actually really shocked to see that it didn't make it into the textbook, but when I started reading about it a bit more, I think that my shock subsided. So M87 is a galaxy that's 54 million light years away. This is what M87 looks like in the polarized light spectrum, so just optically, essentially, and in the infrared, radio waves, whatever you want. As you zoom in on this thing and you start to analyze the image, this is the image that was reported in all of the news media. This is the one that was so well popularized. Now, we have to really back this off a little bit. So I think there was something of a great disservice done when this was released to the media, because what these people were actually imaging was the ring of material, right? This accretion disk around the black hole, which of course neutron stars also share. So what these authors had actually done was they had actually ignored what was happening where the black hole was expected to be shown, filtered away all of the radiation at that point source, and then reconstructed the radiation from the location where the ring structure was predicted to be occurring. And so I think that a much more reasonable headline would have been imaging of the ring structure surrounding potential location of black hole in M87. That would have been a bit more honest, because of course this is what M87 actually looks like, right? It's there's clearly not a hole there where we can't see through it or anything like that. So actually, right after that paper came out, this Japanese group came back with a pretty damning refutation of this study in the first place. And I want to just point out a few things that they mentioned. So, and I recommend, if you're interested in this stuff, that you check out that paper. I'll put it in Moodle for you. So the results that they found were quite a bit different. First of all, one thing they pointed out was that the signal-to-noise ratio of the data set that these guys were using was at best case 1. So what does a signal-to-noise ratio mean? It means that the garbage is, if you have a signal-to-noise ratio of 1, it essentially means that your garbage is as loud as your signal. Now, just to give you guys like some context, when you go and say you get an MRI at the hospital or something, there's of course noise as well in that kind of imaging. The signal in that case is 90% to 10% in an MRI. If you had a signal-to-noise ratio in an MRI of 1, you would be able to see absolutely nothing. It would just look like a big cloud, essentially. So this was the best case of the best pixel resolutions that they were able to pull out had a signal-to-noise ratio of 1. The rest of it was actually far higher, up into the 2, 3, 4, 5 signal-to-noise ratios. This was actually, they actually took a half ton of hard drives worth of data and boiled it down to the point that they actually, the final ring structure that you see there is about 6 voxels, which is, you can think of it as a pixel. It's a unit of location of information. The final image itself is actually, the data from which they pulled this from was actually 1,000 times more. So they filtered out 1,000 times the pixels that they didn't like from the ones that they actually reported. And I don't like this. I don't like this very much at all. And so I think your textbook didn't like this either. And this is why this image didn't actually make it into your textbook. So again, I think the gravitational wave stuff is really quite compelling. I think there's something very interesting happening out there. Whether it has this structure that's been popularized in the media, whether it has this structure that's been reported in this supposed picture of this black hole, I'm a little less convinced of personally. But I would encourage you to read the paper, which, like I said, I'll share it with you guys. OK, so what are people proposing in alternatives? If it turns out that general relativity is just in desperate need of some boundary conditions and something else interesting is happening, what are people proposing it could be? Fundamentally, there's some issues with our conception of black holes. First of all, is light actually being bent by gravity? There is certainly some reason to believe that it's not. Certainly, I would expect that we would be seeing quite a bit of more ring structures when we looked up the night sky. I would expect that most of the stars would have some sort of Einstein rings around them. Secondly, black holes, the theory of black holes results in a negative heat capacity. That means when it takes up heat, it gets cold. This is a very big problem thermodynamically. It seems to violate basic physics. Well, of course, everything about them violates basic physics, which makes them very unattractive, particularly to the quantum theorists. So most quantum theorists will tell you that their quantum picture of gravity will feature no singularities, right? Infinities are unacceptable in scientific theory. And so once the quantum theory of gravity has been achieved most people acknowledge that black holes will turn out to be very real artifacts that result from our misunderstanding of how matter behaves when it's crammed into such a small space. So what are people proposing in alternative? We'll get to that. But what is a black hole? Well, if a body moves around a point that's dark inexplicably, it's a black hole. If bright stars move around a bright point, it's also a black hole if the gravitational constraints are correct. And if a neutron star is too big to resist collapse, it's also a black hole. So the question becomes, is there any observation possible that would refute the idea of a black hole? And I think that's a really interesting question to ask yourself, because under the basic principle of the scientific method, you need to be able to conceive of, in your theory, of some observation which would undermine your theory. This is the basic idea, and then you go and test for it. And it's unclear to me whether there is such an observation, but I think that what it would take to dethrone this concept of black holes is somebody providing an alternative explanation that was as satisfying as what we see, right? You need to come up with a new explanation that's capable of doing this. And is this a new type of matter? Is it a new type of star? Is it a completely new imagination of how stars collapse in the first place, right? Do we need to revisit our idea of how gravity is affecting things at the center of large masses? I wonder about that one myself. So, a very real alternative is going to be the replacement of a collapse model that eliminates singularities altogether. And the quantum theorists are hard at work at this. They propose a few different types of exotic matter-type stars, right? They have stars called Q stars, gray holes, gravastars, strange stars. And all of these stars involve the appearance of new repulsive forces that emerge when some matter is crammed into a tiny little space. Because if you will recall our story of stellar death, at each stage before each one of these explosions, there's the overcoming of some repulsive barrier, right? In a steady state star like our sun, one that's just in perfect hydrostatic equilibrium, these pressures of heat and light are perfectly balancing the gravity, which is causing it to crunch down. And that's why it has this nice spherical shape to it as well. But at some point, the resisting pressures are overcome, right? And it crunches down and it gives off a big burst of material in the process. So the thought that the quantum theorists are working on is that there are new repulsive forces that might emerge at that point where the neutron repulsive forces break down. And so what are those? Well, they're going to involve the appearance of strange states of matter, similar to the degenerate electron matter that we think of in white dwarfs. You're going to end up with degenerate nuclear matter, right? Degenerate quark matter, things like this. And so they propose this whole zoo of different strange stars. You know, I have a quote on this here, but I forgot to write down who it was attributed to. So I'll just summarize it as saying that there are a number of proposals in which these exotic forms of matter would be able to give the same Planckian spectra. You know, you would get the same radiation signatures, the same Hawking radiation equivalent to a black hole. Now, of course, if you think way, way back to when we were talking about, I spent I think an entire lecture talking about the history of the debate concerning the composition of the sun, particularly whether it is reasonable to treat the sun as a ball of gas, which is what we traditionally do treat it as today. And there was this astronomer named James Jeans who argued quite vigorously that the sun was actually a liquid, in fact, not a gas. And there's several arguments that seem to actually support that idea, you know, namely that you can't get a rainbow, you can't get a black body spectrum from a gas no matter what you do on Earth. No one's ever done it before, which is a little bit troubling. And the reason this matters is that liquids are by definition incompressible, okay? So no matter how much you squish a liquid, you're never going to compress it. Gases, on the other hand, and our whole model of stellar collapse is built on the ideal gas law that you can actually crunch gases down together. Now, if it turns out that the sun's structure is something more like a liquid metal than a gaseous plasma, you're in a whole new paradigm of events, right? You're looking for completely new structures all of a sudden. And so, you know, James Jeans famously said that, you know, his model of the sun is not in any danger of collapse whatsoever because liquids are incompressible by definition. So that's something to think about. I mean, another thing to think about here is the timeline of the age of the universe, right? And, you know, a lot of people, you know, I've said this before in class. What do the astronomers mean by universe? They don't mean what you think they mean by universe, right? They don't even, a lot of them don't even realize what they think they mean, unfortunately. A lot of them do, though. And if you talk to some of the more wise astronomers and more wise astrophysicists, you ask them, what do they mean by universe? And they'll say, we mean what we can see, right? And so all of our models that we've discussed in this class are constrained. The boundary condition, the constraint on those models is the idea that the universe itself has an age, first of all, and that that age is very young, actually. It's only about 14 billion years old. And this is a paradigm which is expanding wildly at the moment, and we'll have time for this when we do cosmology at the end, when we start talking about this age of the universe and what it really means. But our entire conception of what is possible in terms of the appearance of what we see in the sky is formally constrained by the age of the universe. So what do I mean by that? I mean that there hasn't been enough time for very many cold things to accumulate in 14 billion years. However, if we take age of the universe to mean the age of the things we can see, and we have the humility to think, well, there's probably a lot of stuff we can't see because it's really far away and it's really dim, then we're left with the possibility that there might be a lot of really, really old stuff out there, much, much older than 14 billion years, right? There might be things that are trillions of years old out there. Now, if you have something big and heavy that's trillions of years old, what's it going to look like? Well, it's going to be very cold. It's going to be essentially invisible to the naked eye, right? It's going to be invisible in the optical wavelength. It's going to be invisible in the infrared, right? But it may undergo gravitational interactions, right? So, you know, there's an interesting there's been some interesting studies about this. One group, I couldn't recall the name for you right now, actually did an interesting model where they said, well, let's take the hypothesized black hole at the center of our own galaxy. Could we just take a bunch of big cold stuff and put it there, and would that have the same effect as this black hole? And the answer is yes, it would. Now, the trouble is, a bunch of pebbles that are very cold and heavy would not be a very stable structure. But something very big and cold would, actually. Now, I would propose to you that the only reason that we haven't really entertained these possibilities to this extent is because the time length necessary to make something big and cold is far more than 14 billion years, okay? And so, the reason I'm bringing this up to you is that cosmology, although it seems like a very remote science, like how could it really ever affect anything to us here on Earth? I think it matters a lot because it constrains the boundaries of our imagination. And I think this is in some sense very dangerous because the concept of universe means a very different thing to you and me than it means to an astronomer. And if we start thinking about universes meaning the wrong thing, if we think that they mean everything that's in existence, we run into applying our boundary conditions to our explanations for these very strange phenomena in the sky. And I think that it takes us down the road towards the mysticism a little bit. So, I don't know. I'm not saying that's what it is. I just think it's quite interesting that these possibilities exist on the edge of what we know. And I think that there's a very good reason for why we are so caught up in the idea that magic could exist and that physics could break down and that the unknown is possible. I think this is a very real thing. My wife pointed out to me that there's this effect that humans display which is called pareidolia. Maybe you guys have heard of this. This is the idea that humans tend to see faces everywhere, right? So this is obviously a tree stump, but you have a very difficult time looking at it and not seeing some sort of emotional experience when you look at it, right? And people see this all over the place. They'll look at wall sockets and so forth. We have a tendency to see what we want to see, right? And I think humans, since the rational period, since the Enlightenment, since the death of widespread acceptance of religion, have been really hurting for a place to find that magic that they really desperately need. And in some sense, I think that looking to the stars has always been the place where humans have found magic. And I don't think it's unreasonable that we try to see those in these anomalous events that we see in the sky. However, I would be very, very surprised if that's where we end up 100 years from now, right? But as we move towards more and more rational explanations for the phenomena that we see in the sky, it's important to remember that there is still a great deal of incredible magic here on Earth, and it's actually in our own lives. It's actually in these questions of consciousness and where do your ideas come from? Did you have the idea? Did you pick it up from somewhere? Where does inspiration come from, right? There's a lot of mystery and magic that remains in biology, which isn't just objects crashing into each other. And I think that it's really important that we steer ourselves back towards that. And one final thing I want to tell you before you leave is that in general, what we've done in astronomy when we don't understand something is we put the word black or dark in front of it. Right now, we're really struggling with how to explain how galaxies are coherent, how they stick together. There's a filler concept right now called dark energy and dark matter, which is undetectable and fills in our understanding. It patches up our theory of gravity so that we can describe the way that galaxies are coherent and stick together, but we can't actually observe it. So what I want you to just remember, the takeaway here, if you hear this idea, dark, black, think, this is a hole in our understanding. We don't know what's going on here, and there's a lot of work to be done. All right, have a good weekend, guys.